Good evening. Welcome. Thank you for joining us for another installment of IEEE and New York Tech's Industry Leaders Lecture Series. Tonight, we'll be speaking about 5G is almost 3 years old, meeting expectations or waiting for more, presented by Dr. Robert DeFazio. Q&A will take place at the conclusion of this lecture. Please feel free to ask questions throughout by utilizing the Zoom Q&A portion at the bottom of your screen. I'd like to pass it over to Dr. Beheshti, Dean of the College of Engineering and Computing Sciences at New York Tech.
Thank you, Rob. Good afternoon, everyone. It is my pleasure to welcome everyone to the fourth session of the Industry Leaders Talk series hosted by the New York Institute of Technology's College of Engineering and Computing Sciences. My name is Babak Beheshti, Dean of the College. This series is co-hosted by our college as well as the IEEE Region 1. Our audience today is composed of IEEE professional as well as student members from across the Northeastern United States, in addition to the College of Engineering's current students and alumni and a number of distinguished guests. I would like to thank the College of Engineering's Dean's Executive Advisory Board, particularly its chair, Dr. Robert DeFazio, who has been instrumental in organizing this series. Today's industry talk leader in this series is Dr. Robert DeFazio, President and Founder, RZO LLC. The talk is titled 5G is almost 3 years old, meeting expectations or waiting for more. Please review Rob's bio sketch available on the event website. Without any further ado, I will pass it to Rob for his talk. Rob?
Okay, thank you, Dr. Beheshti. Okay, so today's talk is titled 5G is almost 3 years old, meeting expectations or waiting for more. And thank you, Dr. Beheshti. Thank you, Tom, Sarah, for setting this up. My name is Robert DeFazio, and I spent 18 years at a wireless R&D company, and the last few years running the R&D department. And the company was a major participant in cellular standards. So I was there through the 3G era, 4G era, 5G era, and even the 6G era. So in today's talk, I'm going to look at where 5G is, what it means to us, but a little bit of a different perspective because I retired 2 years ago and now I have a small R&D and consulting company. So now I'm more of a user and observer than somebody who's actively participating in the standards. Gives me a little bit of a different perspective, and that's what I'll try and share with everyone today. Before my years in the wireless R&D company, I worked for a startup. I also spent 20 years in the R&D department of a defense contractor doing some very interesting wireless work. And one of the perspectives I gained there was just how much of that research and development and how many of those breakthroughs done in government R&D actually were transferred into the cellular commercial wireless industry. So with that, 5G is almost 3 years old. 3GPP is the international body that writes the cellular specifications from 3G to 4G to 5G. And back in June of 2018 was declared a major milestone for 5G wireless in that what was known as the 5G standalone standard specifications were completed. And this really is a huge accomplishment because these standards comprise the work of literally thousands of people from all over the world and is just an unbelievable hallmark of international cooperation. And just to remind myself just how monumental the effort was, I went back and I took a look at the December 2020 drop of the 5G standard. Now, in June of 2018, it was release 15. December 2020, which was the next release, 16 of the standards, there were 1,578 specification documents, active specification documents. That's 1,578 documents, many of which are quite thick and quite detailed. And they include not only the 5G standard, but any 5G devices also need to be backwards compatible with 4G and 3G and 2G. So that's the extent of the effort involved in making this work. And of course, time marches on. There's even the next release, 17, which is planned for March 2022. So today I'll try and touch on 4 topics: the history and brief introduction to 5G. I'll talk about a few things that make 5G unique. Why do we need a 5G since we had a 4G? I'll talk about a few things that interest us now. And when I say us, I mean us, where I'm hoping many of us are users or retail customers of 5G, and ask a very legitimate question: is what is this that makes this interesting to us? And then a couple of words on what we might see in the near future. So, here is a slide showing the history of 5G and cellular standards. So there actually was a 0G, and 0G was an antenna on the highest spot in the city, which communicated all over the city, and a few lucky people were able to get phones and have wireless phone service. 1G was actually the first of the cellular standards, and those phones were in reality FM radios with much like FM walkie-talkies with keyboards, but they established the cellular concept. It established that you could take a finite, relatively small frequency band and reuse it in radio cells and effectively cover the whole world with wireless telephone technology. 2G, there was a move to digital communications. It was a digital modulation and digital voice. 3G corresponded with the burgeoning growth of the internet, and 3G was attempting to provide an internet-like experience to users of wireless phones. And it used a technology called wideband CDMA. It was somewhat successful, but it had its challenges. And you can see in 3G, it was actually partitioned into 3.5G and 3.75G, where a packet access waveform was added to the wideband CDA in the attempt to get up to tens of megabits per second data service. Then 4G, which used a modulation known as OFDM, orthogonal frequency division multiplexing, was just a wildly successful cellular standard. It established the capability of cellular communications to provide a high-speed internet-like experience to smartphones, similar to what you get with a wired internet connection at home. And of course, that aligned with the large growth in smartphones. It aligned with high-speed streaming. It aligned with social media. And that is perhaps the most widely deployed cellular standard right now, and is working quite well. Then comes 5G, and the data rates continue to increase. But there is a question: is what does 5G bring that's different than 4G? And to summarize a little bit what I'll talk about later in the talk, what 5G did is it took a look at the cellular systems and said, we can do more than just talk to smartphones. Let's think of any service that needs wireless connectivity and come up with a cellular system that can support a much, much broader set of use cases. Yes, the data rates will get higher, but let's make it a much broader and wider business. So let me leave you with 2 thoughts from this slide. One is people always tend to look at data rates as a measurement of cellular technology. And if you look at from 1G to 5G, you see data rates go from kilobits per second up to 20 gigabits per second. This is 6 orders of magnitudes, kilobits per second to gigabits per second, over the span of several decades. The second is that each cellular generation tends to live about 10 years. The 1G system was in the 1980s. The 2G system tended to span the 1990s. 3G cellular started in the early 2000s, 4G in early 2010, and now we're in 2020, and we're starting to see the deployment, starting to see the deployment of 5G cellular. Now, this is one of the famous 5G slides that you see in lots and lots of 5G presentations. The International Telecommunications Union, known as the ITU, is the organization that sets the requirements for these generations of cellular technology. And very early on, they came out with this triangle where inside the triangle are all the different use cases that they wanted 5G to address. So of course you see the gigabytes in a second, fast data rates, and the high-speed streaming, but you see a much, much broader application of wireless technology: smart city, industrial automation, smart homes, smart buildings, self-driving cars, augmented reality. And spanning these use cases, they partitioned it into three major categories that were the basic requirements for 5G. The first one at the top of the pyramid is called enhanced mobile broadband. And if you look at the breakout to the left, that's the typical evolution that we've seen in cellular technology. The idea is to get the data rates up very high. And so you see peak data rates of 20 gigabits per second. And then the other parameter that tends to be very important from the air interface is latency. So now you see latency of 4 milliseconds, which is the time it takes to get a message from your phone up to the network. Typically in early generations, you would have seen hundreds of milliseconds. In LTE, 4G, you may see 20 to 30 milliseconds. So it is indeed a tall order. The second major category is called ultra reliable and low latency communications. This is a mode that's geared towards mission critical type communications. And the best example of that we see nowadays is the talk about self-driving cars. And the importance here is not so much the data rate, but the speed and the reliability. So the challenge here is to be able to send a message that allow reaction time in the times machines would react in, say, 1 millisecond. But along with a latency, you also have to talk about reliability. So it has this requirement for 99.999% reliability, which again is a pretty tall order for a wireless system. 99.39 reliability in 1 millisecond, yet it's what you need if you're going to use it for mission critical safety applications, say self-driving cars, say e-health, things where safety and loss of life may be involved if the messages don't get through and get through correctly. The third scenario is called massive machine type communications. Now this one, in truth, has been a little bit de-emphasized in 5G because it's IoT, smart city, and the fact is that 4G has a quite capable IoT waveform known as NB-IoT. It stands for narrowband IoT, which is working quite well. So the emphasis in 5G has really been on the enhanced mobile broadband and the ultra reliable low latency communication. Massive machine type communications will come, but at the moment, 3GPP, the specification setting body, has actually taken this narrowband IoT, and when it proposed to the ITU what the 5G system would be, it's a new system for enhanced mobile broadband and ultra reliable low latency communications, but it includes narrowband IoT as the massive machine type communication waveform. So let me take a moment and just talk about a very simplified 5G network. So if it's a cellular network, of course, there are devices. There are cell phones. If you're doing industrial automation or vehicle-to-vehicle communications, you might see vehicles, you might see sensors, you might see anything that wants to connect to the network. Yeah. Then you have the air interface. This is the radio connection that goes to and from the devices. If you have a 4G device, you'd be connecting to a 4G or an LTE base station. Now the base stations will connect to something that's called the core network. The core network is basically a computer system that does things like provisioning, billing, quality of service, and it connects to the outside world. Now, when 5G was introduced, in order to introduce it fairly quickly, well, there would be a 5G air interface and 5G devices, and they would talk to a base station that has the 5G capability, but there was a mode that was called non-standalone, and the 5G system would talk to the 4G core network. And most of the 5G deployments that are out there right now are in fact this non-standalone mode. What it means is that you get some of the capabilities of 5G, but you don't necessarily get all of them. You know, for example, latency. You won't get the latencies that you expect with 5G because you're going through a 4G core network. Now, the holy grail of 5G is to connect to a 5G core network. So if you have a 5G device, you'll connect to the 5G base stations. And there's an awful lot of acronyms in these systems. So base station is called the transmission and reception point. Believe it or not, the 5G radio is very simply called the new radio. So you'll see this abbreviation called NR. And the 5G base stations is now connected to a 5G core network. And one of the distinguishing features of the 5G network, core network, is the goal is to make it just look like a cloud-based server farm with commodity servers. So now you get a cloud-based server, and it's very much software defined and software configured, as opposed to a lot of proprietary hardware and software that was used in previous generations. Now, another important aspect of 5G is when you're trying to achieve the very, very low latency is this concept of edge nodes. If you want low latency, there's just physical limitations that say you need to be near the radios that you're communicating with. And so you build out small cells in the local area where the communications will take place. And this is the whole topic of mobile edge computing, which is the topic of the next talk in this industry lecture series. So I'd encourage you to tune in there, where an executive who runs R&D at Verizon will in fact give a deep dive into mobile edge computing. And then of course the ultimate goal is to take the connection and connect to the outside world, either the internet, which is where most of the traffic goes these days, or to the landline phone network for phone calls, or to connect to other cellular users. So what about deployment? 5G is out there, and we all see the advertisements where operators are talking about their 5G networks. And there are a number of websites and companies where you could actually check out what these deployments are. The map on the right, if you happen to go to that website, which shows 5G locations, you could zoom in and you can actually see where there are 5G base stations in your neighborhood. Now, to summarize it a little bit more, there are organizations that will tell you exactly how many 5G deployments there are worldwide. So right now, you're looking at 163 deployments throughout the world, which is a big number, but it's not quite as big as 4G. If you add up LTE and LTE Advanced, which are two flavors of the 4G cellular network, you see about 1,000 deployments. And then the other metric that you might look at for 5G is how many of the devices out there, primarily smartphones and tablets, are 5G capable devices. And as we discussed a moment ago, the typical cycle is about 10 years. And we're somewhere between year 2 and 3. And in year 2, 5G is actually doing a little bit better than 4G did. About almost 21% of the devices are 5G compared to 15% for 4G in the second year. But to become a network that's truly taking advantage of 5G, you're really looking at trying to get out to year 4 or 5, where more than half the devices are 5G devices, as opposed to legacy 4G devices or 3G devices. Now, a cell phone is a radio, and for me, who has a history as a radio engineer, it's very interesting to talk about what radio frequencies do these 5G cell phones work in. And if we go back once again to the 3GPP standards, you find in the standards there are 54 frequency bands. Now, this is for international operation, and a lot of them are overlapping, but they're broken into two major categories. The first category is generally called sub-6 gigahertz or mid-band, sometimes called FR1. And that encompasses a lot of the legacy frequencies that have been used for cellular radio systems. The low end is at UHF, and in fact, those are frequencies that historically have been used for TV channels. The nice thing about these lower UHF channels is that the propagation is very nice. The signal will travel far, the signal will bend around obstacles, the signal will go through walls and into buildings very easily. So they're considered very, very nice frequency bands to use for cellular mobile communications. On the other hand, because they're low frequency bands, the bandwidths tend to be smaller. And if the bandwidths are smaller, the data rates are less. Well, at the high end, and this is going up into the low gigahertz range of frequencies, the propagation starts to get a little bit more challenging. The radio signals tend to want to go straight. They don't want to go through things. They tend to reflect instead of going through devices. They don't diffract around as well, but it's still quite workable. But the huge advantage is the spectrum available and the bandwidths are much larger. So now you see systems that could have 100 megahertz bandwidth where you could pump much, much higher data rates through these channels. Now, the second group of frequencies are known as millimeter wave, and I'll have a lot more to say about that in a moment. It's called FR2, and these are a new range of frequencies in 5G that are up in what's called the gigahertz region, which is 24,250 megahertz or 24 gigahertz up into the 50s of gigahertz. And now you're seeing bandwidths that are getting up as high as 400 megahertz. Now, as far as use in the United States, the operators in the United States have frequencies in all of these bands, from the UHF band all the way up into the millimeter wave bands. And the operating bands tend to have these N numbers. And the way it works is the FCC in the United States auctions these frequency bands, and the operators bid on licenses, and they're considered quite valuable. As an example, a few months ago, there was an auction for the 3.7 to 3.9 gigahertz band, and the government raked in $81 billion from operators who bid on licenses for these frequency bands. So they're highly coveted and they're highly valuable. Now, another interesting question to ask is, well, what about my telephone? And truth is, as a consumer, you really don't need to worry too much about this. But if you're the type like me who likes to dig into the specifications, you can find out. So if you go to the web page for the iPhone 12, for example, you find that the iPhone 12 is compatible with a lot of the 5G new radio bands, and it lists all these bands here, N1, N2, N3, N79, N66, and it's compatible with all these bands that the US operators use, as well as the bands that many international operators use. And then also take a look at this. It also has in it frequency bands for 3G operation and for 2G operation, because every phone needs to be backwards compatible with the previous generations of standards. Now, millimeter wave, when people talk about one of the major technology advances in 5G cellular, it's the use of these millimeter wave frequencies, which opened up just hundreds and hundreds of megahertz of bandwidth for cellular communications. So that brings me to the next topic: what makes 5G unique? And the millimeter wave frequencies is indeed one of the things that makes it very unique. Millimeter waves have been used in systems for years, but a lot of them were perhaps government systems and long-range line-of-sight systems. And there was a lot of skepticism as to whether this would work in the cellular environment. So there were a lot of studies, there were a lot of experimentations, and truth is, the propagation theory actually predicted that this would work. And there were limitations to it, in that it tended to be short-range, dense deployments, that you had to be careful in your expectations if you had an outdoor cell and you wanted to transmit indoors. It would diffract around obstructions, but nowhere near as much as the lower frequencies would. But one of the things it would do is reflect off things and create multiple paths, which started as a single path. So the real challenge turned out to be the manufacturability of millimeter wave components. Can they be made small enough that would use a low enough power at a low enough cost to make them practicable for cell phones? And that was the challenge. And part of that challenge is they required something called phased array antennas. Antennas that were comprised of multiple elements where you feed each element or a small group of elements individually so that you can steer the radio signal to where all those reflected paths are coming from, or even steer it to multiple reflected paths at once so that you can gather all this energy. And in fact, it was quite successful. And if you look down here at the lower right of the picture, this happens to be a phased array for smartphones. It's not so difficult at the base station side, although not easy, but in the smartphone, to miniaturize one of these millimeter wave phased arrays was quite an accomplishment. And this happens to be a photo of one made by Qualcomm. And you'll find in a millimeter wave phone, typically 3 of these things. And that's where, in my opinion, the huge millimeter wave technology breakthrough came from. Not from the ability to use the millimeter wave frequencies so much as the ability to manufacture these millimeter wave components in quantity with the required reliability with the low power. Now, it turns out since this work now, the FCC has auctioned 4 or 5 bands of millimeter wave frequency and has auctioned 5 gigahertz, approximately 5 gigahertz of millimeter wave spectrum. Now, keeping in mind, if you go back to the early generations of cellular, there might have been 40 or 50 megahertz total of bandwidth available. A little bit before 5G came out, there was a time when there might have been 500 megahertz of total radio spectrum available for cellular systems. So by introducing the millimeter wave frequency bands, this amount of spectrum has jumped up by almost a factor of 10. So this is what makes this huge quantity of data transmission possible. And this is one of the major breakthroughs in 5G. Another technology that can potentially help is Mimo. That stands for multiple input, multiple output. The theory and the implementations have been around for several decades, but in what's called low-level MIMO. MIMO means you put multiple antennas at the receiver and multiple antennas at the transmitter with the theoretical goal, in simple terms, of scaling the data throughput by the number of antennas. So if you could put 2 antennas at the transmitter and 2 at the receiver, you would hope to double the data rate. If you put 4 at each, you'd hope to multiply it by 4. Well, in 5G, as you go up to these higher operating frequencies, the antennas get smaller. If the antennas get smaller, you could put more and more antenna elements into an antenna and still have something that's a reasonable size to deploy. For example, this figure shows an antenna that has 64 elements, which really would have been unheard of in the early generations of cellular because this thing would have been far too huge to deploy. So the term now becomes massive MIMO, where you use lots and lots of antenna elements. And the concept is to put the complexity associated with massive MIMO at the base station, where there's more room for heavy processing and there's more power available, and try and make the complexity as simple as possible at the handheld terminals. And the promise is there to get to 10, 50, 100 bits per second per hertz. So this is an area of activity in an area which promises to use the spectrum even more efficiently and turn the data rates up even higher. Now, we talked a little bit about how one of the advantages of 5G is that it opens up cellular wireless communications to this broader range of use cases, to industrial automation, to vehicle, to IoT, to extreme low latency. Well, at the same time, one of the concepts was well, can we also open up the architecture of these systems, make them a little bit more open to introduce the possibility of additional vendors providing their products into the infrastructure? In earlier generations of cellular, it was very often a cellular operator would team up with a small number of infrastructure providers who would build all the hardware, provide all the software, and the term that was used was walled garden, because no additional vendors could become part of this ecosystem, unless they happened to be partnered with the infrastructure provider. And from the operator's point of view, it was difficult to change vendors and to introduce new capabilities because of the tight coupling with proprietary hardware. So in order to serve a broader business base, the thought was, can we open up this system and make it possible for more vendors to participate? So two examples on this slide. There's an industry organization called the O-RAN Alliance. Concept there being that the 3GP specifications are a great set of specifications, but can we add some more open interfaces and an architecture that would allow other hardware and software vendors to supply components to the cellular infrastructure in such a way that they can all work together, and that there's a variety of vendors that can provide the services to the cellular operators. On the other side of the slide, there's an example of a virtualized RAN software provider. This is effectively a software and integration company that will put together a network. And if you take a little close look at this, notice what you find in the core network is COTS x86 hardware. So the core network does indeed become like a commodity server farm, much like a cloud server, where software runs on the server. Even the hardware can be bought from multiple vendors, integrated together. And so now you have this open ecosystem of component and software providers. And if you think of it, it not only makes the system perhaps lower cost because of competition, but it now also opens up the possibilities for smaller companies and even perhaps individual entities to build their own cellular systems. The idea of a private cellular network was really not something that was particularly practical in the days of 2G and 3G. Well, in the days of 5G, with open interfaces and an ecosystem of many vendors who can provide components, this all becomes possible. Another concept here is the idea of network slicing, which is really a kind of a fancy word for virtualization. So think about the different services that are provided, some being high-speed data. Maybe one is an IoT service where hardly any communications is used until, say, a sensor detects something. Maybe there's an operator who wants to sell their own branded cellular services, which perhaps have certain particular services, not the highest data rates, but perhaps easier to use, each with their own requirements. And now you take this software-defined system that's running on the server farm, you virtualize it, and you build these things called slices, where each slice can service a particular use case. So with the commodity hardware and the software defined operation, you can service all the use cases, and at the same time you can define a set of APIs which allow the operators of these services to configure their own slices for their own parameters and service their own customers' needs. So the one word that I would say distinguishes 5G from the earlier Gs is flexibility. It's got an air interface that can operate in frequencies from UHF to millimeter wave, from data rates that are near zero up to gigabits per second. It can use commodity hardware for a lot of the network infrastructure. It can use software reconfiguration for a lot of things. So it opens up both a broad case of use cases to anyone who could think of a business that needs wireless services. Now 5G would aspire to be the system that can provide that wireless service. And at the same time, it has the possibility to introduce a lot of more vendors into the ecosystem that builds and implements the network. So if we get on to the third topic, what should interest us? And by us, I mean the current users of 5G, because a lot of these things are talking about the business aspects of 5G and a lot of things that may be not quite deployed yet and perhaps not something interested to a retail user. So let's look at something first, basically the performance of what's out there. And frankly, if you're into really high data rates, the performance is amazing. If you can find a 5G millimeter cell and connect to it, look at the data rates that are available. Yeah. You see 640 megabits per second data rate using a 5G millimeter wave link. Now, I guess it's not totally clear what you do with 640 megabits per second, but it actually works. And in terms of high-speed streaming, perhaps setting up hotspots, it's an amazing capability. And I'll talk in a few minutes about one of the scenarios that it is quite useful for. But generally, if you take 5G and you go back to the sub-6 gigahertz, you're seeing data rates in the 60 megabits per second. Now, people always like to talk about records, and one of the recent records that was advertised was 5 gigabits per second. And this was done, of course, with a millimeter wave frequency. So the folks who put this together used 800 megahertz of bandwidth, and then they used a technology called carrier aggregation to combine that with two 20 megahertz 4G channels and got a 5 gigabit per second data rate. And another interesting tidbit about this, if you take the 5 gigabits per second divided by 840 megahertz, you get 5.9 bits per second per hertz, and that's the Mimo operating there, getting lots of bits per second for every hertz of bandwidth. Now, if we ask a more perhaps down-to-earth question is, well, what will I get typically if I have a 5G smartphone? And there are companies that make these measurements. And you see, if you had your 5G smartphone and you turned it on in New York City, where these particular measurements were made, well, you may connect to a 5G cell. You may connect to a 4G cell. If you're unlucky, you may connect to a 3G cell. But the typical user experiences tend to range from 40 to, say, the high 50s, almost 60 megabits per second for the downlink from the base stations to your devices. If you're talking about uplink, the numbers are smaller. But in fairness, the numbers are smaller, in the 10 to 20 megabits per second, because most of the demand is downlink. So the systems are provisioned to provide more in the downlink than the uplink. As far as latency, if you recall, the goal for 5G for the enhanced mobile broadband was 4 milliseconds, and it's not really there yet, mostly because what's been deployed to date are these non-standalone networks where the radio is 5G, but the actual base station is a 4G base station. So you're seeing a little bit improvement between 5G and 4G, but you're not going to see the really fantastic latency numbers until you have a standalone 5G that's widely deployed. So another question I often get is, well, should I go out and buy a new 5G phone? Well, my answer is, well, sure. I mean, if you need a new phone or you want a new phone, you're going to get a new super fast multi-core processor. You're going to get a nice clean set with lots of new high-speed memory. You're going to get an amazing display, amazing OLED display with high dynamic range. The cameras are just getting better and better. And every time you turn around, they add more lenses to the cameras in the back of the phone. The sound is better. The security is better. The battery life is longer. So sure, go and get a new phone. But of course, the real question is 5G is giving you this data rate in the 50 to 60 megabits per second range. Is that a good reason to buy a 5G phone? And I suppose it may not be right now unless you have really a need for those high data rates. If you have a good 4G connection and you're getting 30 or so megabits per second to your phone, that's a pretty good connection. Now, if you don't have a good connection right now, I would venture a guess that it's not so much because you don't have a 5G phone as it is because there aren't cell sites deployed or there's a lot of interference that's preventing you from getting the really high data rates. So 5G does have a lot to offer, but if you're looking at yourself as a smartphone user, you really have to think about how many megabits per second do I use and what am I using it for? Now, another interesting question is one time I gave this talk and a gentleman in the audience stood up and said, "Can I cut the cord? Is it time for me to cut the cord?" And I thought that was a very interesting question because maybe that is the ultimate question about 5G. Can I get to the point where all I have is a 5G, all I have is a mobile phone cellular subscription that may be 5G, and that's it? And will it meet all the needs for me and my family? Well, in terms of cutting the cord, I came up with 3 answers. One is if you mean what most people mean today, that I'm going to have a mobile phone subscription and just a high-speed internet connection to my home. Basically, you get rid of the landline phone and you don't subscribe to cable TV channels. Then the answer is, of course you can, because lots and lots of people do it. Hard-pressed to meet a young person starting out who does anything other than get a high-speed internet and a mobile phone. But the more ambitious question is, can I just get a good mobile phone subscription and use that for my whole family's talking, testing, streaming, gaming requirements? Not so sure, and we'll talk about that on the next slide. However, 5G also has this millimeter wave fixed wireless access capability that's very interesting and in a sense is another way to cut the cord. So, let's talk about this cutting the cord with just a mobile subscription. So, it's not rocket science. I have my phone. My phone has really high data rates, so I tether it to my large screen TV. And if I'm asking the question as to whether this will work or not, well, I go to the Netflix website and it says, well, 25 megabits per second. And I think, well, hey, that's easy. 5G can do that with no problem. The data rates are there. It's far more than we need, so maybe it will work. But the catch really is that the mobile networks are not at this time designed for the quantity of data that this will demand. A typical mobile user with a smartphone or a tablet might use tens of gigabits per second a month. A typical high-speed home internet connection where you have a large screen TV and you like to watch sports or you like to watch high-definition movies, or you have gamers in the house and you have multiple screens, you're looking at hundreds of gigabytes per month. If you dig a little more into the Netflix website, you'd see a high-definition movie uses 3 gigabytes per hour. So although you could get plenty of data rate if you have a good 5G connection, it really comes down to reading the fine print in your contract. So if you look at this particular AT&T unlimited plan, and they're pretty upfront about it, 30 gigabytes of hotspot data per line. And if you dig way down into the fine print, you find after 30 gigabytes, your speed is slowed down to a max of 128 kilobits per second. If you look at the T-Mobile offering, well, you get 40 gigabytes, and these are unlimited plans, mind you. The 40 gigabytes, after that, they can slow the network down to a 3G speed. I'm not sure what a 3G speed is, but maybe it's like 128 kilobits per second. And the higher speeds are reserved for smartphones and tablets. So what does that mean? Well, if I'm watching high def movies at 3 gigabits per hour, 3 gigabytes per hour, that's 10 hours of watching, which is not very much for the month. And the networks are just not designed to do it, and they just can't quite do it yet. So if you're going to try and cut the cord and you like large screen TVs and high definition and sport, I'm not sure that it would work so well right now. However, there is one more capability of 5G, which is interesting. And again, it goes back to the millimeter wave technology. And the technology providers realized that, well, you know what, this millimeter wave, which can provide hundreds of megabits per second, if I put a little millimeter wave base station on, say, a lamppost, well, I can then beam the millimeter wave signals to houses at hundreds of megabits per second and provide a service that pretty much looks like a cable service or a high-speed internet connection to the home. And the issue with millimeter waves going through buildings is solved by, well, the customer equipment looks like a very simple user-installed device, that's put by the window, that picks up the millimeter wave signal, turns it into Wi-Fi, and beams Wi-Fi into your house. And so now you have a 5G wireless, based on millimeter wave technology, high-speed internet connection. And if you use that along with your mobile phone service, have you cut the cord? And in theory, I guess you have cut the cord, but on the other hand, it's still 2 subscriptions. So there were those 3 options on the few slides previous. It's really not that much different than the first option, where you have your mobile phone subscription and a wired internet connection, but you've now replaced the wired connection with a 5G millimeter wave fixed wireless access. So now this is quite an important and an interesting technology, because in neighborhoods that don't have wired internet, here's a solution. In underserved areas that don't have a cabled high-speed wireless internet, here's a solution. In a neighborhood that perhaps only has one internet provider, here's a solution to provide some competition. So it's an important technology, but then again, it's not a mobile technology. It's an additional separate use of 5G technology. Now, I can't talk about 5G without saying something quickly about vehicle to vehicle, because when I think about what could be a killer app, and vehicle to vehicle communications has so many applications, and it's actually not only vehicle to vehicle, but vehicle to everything. Vehicle to vehicle, vehicle to pedestrian, vehicle to infrastructure. And if you think of all these things that could be done with that, cooperative safety systems, cooperative cruise control, autonomous or semi-autonomous driving, autonomous navigation. This is one of the places where wireless is a key component of the system and could really make a difference in the transportation systems between safety and traffic. Now, there is a competing technology, it's called DSRC, that has been known for many years, but 5G is making a very, very big technology push in this area. And it's a place that perhaps can become a revolutionary and killer app for 5G technology. So just a couple of quick words on what's next. Well, for 5G, the biggest next thing is to continue deploying 5G and to move up on that 10-year cycle where the devices and the networks are primarily 5G. There's spectrum sharing technology, which I didn't talk much about. There's deploying the advanced features like network slicing and mobile edge computing. And then, of course, the standards are going to march on. There's Release 17, which is coming in March of 22, and there's a plan that's expected early in 2022 for Release 18. And then finally, new use cases. Satellites is a source of wireless technology. There's a number of companies that are launching large collections of low Earth orbiting satellites. You see a lot in the media about drones being used for delivery. Well, those drones need to be need to have some sort of wireless connection to monitor them, to control the safety, to determine where they can fly and where they can't fly. There's another application for 5G. The other figures on this page start to move a little bit into 6G, things like holograms and digital replicas, extended reality, use of robots, and even going up to higher frequency in the terahertz are 6G research areas. So with that, I'll stop the presentation, and I think we have a few minutes here if there are any questions. So Sarah, let me turn the control back over to you.
Thank you. It looks like we have a few questions.
Okay.
Okay, I'll go from the top. What 5G benefits does a user really get in a non-standalone 5G deployment?
That's a good question. In a non-standalone 5G deployment, I'd say there are two things. One is that I'm not an operator, so I don't know what their strategy is for deploying 5G, but I would guess network operators are constantly trying to enhance their coverage. So one of the things they'll do is try and improve the coverage by deploying new infrastructure. And of course, the new infrastructure would be 5G infrastructure. So places where there are coverage holes and lower data rates, that's one advantage that you get with a 5G non-standalone, is just better cellular coverage that can provide higher data rates and service more people. The second one is frankly just simply the higher data rates, because although on an individual basis, perhaps the higher data rates are not so critical. Remember, it's a shared resource. So if you double the data rate, maybe it's not an individual that's getting twice the data rate, but you can service twice the number of people. So if you're in a community that's a growing community where lots of houses are being built, where there are apartment buildings being built, and a lot of people are moving in who want to use their cell phones, those are the advantages. But in all honesty, you could probably make a very strong argument that, hey, you could have done that with 4G. So it's really these other aspects of 5G that I would say are the important things that distinguish 5G from 4G in the previous generations. But very good question.
Another question, can Starlink project might end up as a monopoly in providing 5G networks, since they're going to be able to provide data transfer under one company to everyone in the world? Especially, it is important to have 5G accessible at any point if we're going to connect our autonomous cars, which carry a risk of accident. In the case of disconnection that we face frequently in conventional cellular networks.
Okay, I'm not sure, that almost sounded like two questions, or is it if it's a question about, is it a question about vehicle to vehicle? I'm not sure I completely understand it.
They're asking if Starlink project might end up as a monopoly in providing 5G.
Oh, okay. So, in other words, do you need one service provider if you're doing vehicle to vehicle communications to provide 5G coverage? Perhaps that's the question. And, I don't necessarily believe that anything has to be a monopoly, but with vehicle to vehicle communications, in my opinion, it's going to have to get somehow endorsed by the municipalities, because I think it's going to work best if there's infrastructure that's built along the major roadways. So, to the extent it's a monopoly, I think in particular areas, I would imagine that there'll be particular companies that win the bids and get to build out in a particular area. But I can't imagine there'd be a situation where one company gets to cover the whole country. But the beauty of standardization, if they are compatible, the whole point of standardization is that you can buy equipment from multiple vendors. And the reason that standardization makes things cost effective is because of the competition. So, I guess I'm a little skeptical about monopolies anywhere. But I do realize that if you're trying to do something in a particular geographic area, there is, certainly an advantage to go out for a bid process where one company gets the contract.
Another question, with the technology we have today, what are changes another 20 or 30 years of development might bring us? Will it be worth the invested time and money?
That's another, yeah, that is really a great question, because you start to ask the question, is it going to plateau, right? And, there was an awful lot of discussion about that during 4G. In fact, there was a book that came out that was called The 5G Myth, where somebody was, thought that the standards bodies and industry were selling people a bill of goods with this 5G stuff because 4G was just so darn good. And with 5G, as we talked about, 5G they cranked up the data rate, but they also said, well, let's come up with a system that broadens the use of wireless so that anybody who can imagine any sort of service that needs wireless technology can go to a network operator and say, give me these capabilities, whether it's high data rate or low latency or intermittent communications, whatever, whatever it is. And so, that's where the big promise of 5G is. Now, if you look at 6G, and there is a lot of 6G research going on, it's really a very, very exciting research area. You start to see the areas that, you ask those questions about what will happen, and we didn't spend a lot of time on it, but you see things like holograms. So do you believe that holographic communication will be something that will be interesting to people? And if it will be interesting to people, if you look at the data rates necessary to communicate real-time holograms, it's really, really large. You really want to imagine something into the future. Look at what's going on with the promise of commercial flights into space. Well, those folks are going to need communications, and it's going to be wireless communications. So is that going to be 6G or is it going to be 7G? Who knows? Robots. Imagine if robots or drones are all over the place. If you look up in the sky and you see drones that are delivering packages to everyone, they have to communicate with each other. If they don't communicate with each other, just imagine the chaos that would happen. So, in 20, 30 years, if the question is, will things change? Yes. Do I pretend to be smart enough to be able to predict? No, but I guess I can imagine as well as anyone else can. So, it marches on, and to the extent that wireless will need new capabilities, yes. Will it eventually start to plateau a little bit? I think a little bit too, but at the moment, there's still plenty to be done.
And then I think we have time for one more.
Okay.
And this goes along. So what are the major constraints that were found during 5G deployments, and any lessons that could be used for 6G?
I think one of the major challenges with 5G was really a little bit of a disbelief in what the theory was predicting. I talked a little bit about millimeter wave communications, and I know early on there was a lot of theory that said this should work. In fact, an interesting story is one time I was in the lab in one of the company I worked for, and we had a millimeter wave link come, and one of the more senior engineers came and said, that's never going to work. You're never going to be able to do that with millimeter wave. And he went and got a water bottle, because one of the other things that millimeter waves historically has had problems with is rain and snow. And so he got the water bottle and he started spraying it in the air. And you see, it's going to stop the link. And, we were all smiling because we knew it wouldn't, and it didn't. But, there was almost a little bit of skepticism in what people could actually achieve. To me, I was looking at it and thinking, well, this will surely work, but is somebody going to be able to build this cheaply enough? So, I think just don't give up on ambition and optimism and what a group of very, very determined people can get done. And, that's my suggestion for when you look to 6G or 7G, or for that matter, any technology advance. So, I guess that's it. Are we out of time, Sarah?
Yeah. So we're about a little over 6 o'clock. So
Okay.
thank
Well,
you.
Sarah, Tom, Dr. Beheshti, thank you very much. It was a pleasure to be able to give this talk. I hope folks found it interesting.
Thank you. Thank you, Robert, for a great talk. Also, great questions. Thanks for being a great audience. Thank you all for participating in this event. My thanks go to colleagues who made this event happen. Dr. Rob DeFazio, Assistant Dean Jane Polizzi, Ms. Carmen Marmo Savinetti, and of course, our irreplaceables, Ms. Sarah McCoff and Mr. Tom Leggio. Please tune in for our next talk on April 26th, 5 to 6 p.m. by Dr. Sanugita Shamsunder, VP of 5G Digital Ecosystem and Innovation at Verizon. She will be presenting a talk titled 5G MEC Mobile Edge Computing and Related Applications. Until then, be well.